All right, we should be live. Excellent. So I'm just going to start, even though there's nobody in here. But what I'll say is today we're going to be building a hash table. Let me take off these headphones. Now, what is a hash table? Well, a hash table is usually, you can think of it as a pair of keys and values that are stored somewhere in data, like you might, stored somewhere in memory rather. So you might use them in a language like this. You'd say something like table, and then maybe some square brackets, depends on the language. And you have a string, which would be my key, something like that. And you say equals some kind of data, my variable, whatever that could be. That's how you might usually, see a hash table in, depends on the language. But it's usually a pair of keys and values stored together, right? So, with that in mind, we've got to find somewhere to store the keys, which would be strings, somewhere to store the values, which would be some user-defined value type, and also to make the lookup fast, what people usually do, that's why it's called a hash table, is they hash the string, so they hash this value here into some kind of number, and the number will be an index into an array, which will make the lookup pretty much O of 1 minus however long it costs to do the hash function. So from memory, I haven't actually implemented a hash table for about 5 years, and I've only done it once. So that, I think there's two types. So one is, let's just draw some lines here. Let's say we've got, what is that color? Give me a better color, please. Is that not? Okay, I don't like that. There we go. All right, bit of a thicker line. Actually, we'll just use a box. Okay, so we've got, let's say an array. We can just pretend this is an array. Just gonna copy this line. Well, I thought I was gonna copy it. What is happening? Okay, well, something very strange is happening. So we can imagine we've got something like this in memory, okay? And then we've got in here, these are our slots for our data. So we're going to have data, my variable 0, 1, 2, 3. I don't know why it got thick all of a sudden. Oh, because I changed the stroke width. 2, 3, 4, 5, 6. So you could just say this is an array, right? And then let's say we hash our key. Okay, so we hash our key into a number. So a hash function is a function that turns some data into some other kind of data, in this case a number. So we hash it into a number, and then we make sure that number fits within this range by using a modulo operator usually, and then that'll give us an index. So we'll say hash key, and then we put key here. So key goes here, and then the value, let's just say somehow we can also fit the value here. Don't have to worry about how this is laid out yet. Okay, and then we have another thing we want to enter. Let's say QOP, whatever that is. QOP, okay, we hash that, we put that here. And same thing, another value. And then let's say we do ABC. Don't know why these are all 3 letters. They don't have to be the same character length, but let's just say. And then this one also comes out as 3. So we've got a problem. We've got a collision. This is called a collision. Okay, why did the NVIDIA GeForce Experience just come up? Like, why does that happen? I keep disabling that thing. Anyway, so we've got a collision, and that means we can do one of 2 things as far as I remember. So I decided I don't want to look this stuff up. I just want to see if we can figure it out from the principle of the thing. But I do remember a little bit about it. So we could either have in here, we could have a pointer to a next, which would be somewhere else in memory, right? So we could have another box which has the key and the value. Don't worry too much about how this would actually be stored. This is just conceptual. And then also a next. And then that might point to somewhere, but probably nil for now. Okay, so this is called chaining, I believe. And so these things would be called buckets in this version of a hash table, I'm pretty sure. So you'd have bucket 0, and it might have just the one element. And then as you add more elements that collide with 0, you get this sort of linked list that just becomes longer and longer. And obviously, well, not obviously, but depending on how your linked list is stored in memory, this could become very slow. It could, it depends. If you could do some things to make this quite fast, but let's just say that this is the slower version. Okay, so what you'd usually want to do is size your list of buckets or your array of buckets large enough so that you have not many empty spaces or 0 empty spaces and not many links in the chain or 0 links in the chain. Now, of course, for a general purpose solution, you can't really know the bounds of everyone else's program. So when you're making a general thing, you've got to use some, I guess, general heuristics to figure out what's a good, decent, like a good default size for most common operations or most common data. So we're not going to use this one, I don't think. I want to try another one, which I think is called open addressing. So if we pretend we've got another list, can I copy this one? Let's have a look. Please let me copy things. I think because I'm using a tablet and a mouse, it's just messing up. I don't know what's going on. All right, I just have to draw another one. That's fine. Okay. Yeah, you have to excuse the horrible drawing, but you get the idea. We'll just leave it as that big. Okay, so this one is called open addressing, if I'm remembering correctly. All right, and so same thing. We're going to hash these things, and we're going to put, let's say I put key here and the value, and then quop is in 1, and then ABC is going to collide with key, right? So we've got a collision here again, but this time, instead of having a linked list, we actually just go down this list until there's an empty slot, and then we would put ABC here. So now the trade-off is when we hash this key and we look it up, so we want to say like, maybe we'll call it a map, so map get or something, and then we'd pass in our key, ABC, probably pass in a map as well, but anyway, let's just say that, map get ABC. So what we'd actually find is that as we're in this get function, we would end up here first, and then we're like, okay, we're going to match this key. Key is not the same as ABC, therefore we should go to the next one, and then we find it, right? But it could be that we have to wrap around back to the top, because it could have been up here, or it could have been here, right? Could have been one above, and then we'd have to go wrap around back down, and then we'd be doing a linear search basically. So we know linear search is usually very fast because of locality of data in the CPU cache. Just ignore this text here, that's from something else I was doing. If you don't know anything about the CPU cache, well, I will give you a very simple example that might not be 100% accurate, but let's say this is our CPU here, and it's got all the processing, it's got all the cores and stuff right here. And let's say the actual CPU is like this big or something. And then in the CPU, like on the CPU, next to it, next to all the processing units and stuff, you'll have these little blocks of memory. And these are called caches or caches. And there's 2 or 3 levels, L1, L2, L3, and they get larger and larger. So the smaller ones are the closest, and then L2 are a little bit further away, and then L3 are the furthest away. But they're also the largest. And so basically, by putting all of your data in an array, you get to have the CPU fetch. So when it fetches this memory, it's like, oh, you want to use, you want this this hash table data. Okay, you want this. Okay, I'm going to grab, this, the thing you requested, which is the start of the hash table probably, and then as many bytes as can fit, or as it will do. I don't know actually how much it will be, but usually each line of a cache is 64 bytes if I remember correctly, and I think the whole L1 cache is 128 kilobytes or 256 kilobytes. Anyway, it's not very big. And then the L2 can be like 8 or 16 megabytes, and the L3s are getting pretty huge nowadays. But point is, the CPU is like, okay, I'm going to fetch this and all this other data around it because you might want to use that. That's why arrays are so fast these days. Even though, like for example, you might want to use an algorithm, some kind of, let's say you're using some kind of graph. Well, I don't know if this is a good example, but let's say you have an algorithm here that's like, ostensibly faster than traversing every node. So you could have like an O of n squared, I think, like they're all connected or something. And then you find out that if you use an algorithm where you actually just linearly search every node because they're actually all next to each other, so it's much faster. That's because of this caching thing, right? So yeah, just something to think about. Anyway, for our purposes, we're not too worried about this right now. We just want to actually get a working hash table. And since I don't know anything about hashing, our hashing algorithm is going to be crap, but we can always fix that later. That's fine. As for the data layout, I'm not exactly sure. So something that you might want to do in a lot of instances when you're using a hash table is do something like you probably see this in some languages, right? Key value, like this is in Odin, for key value in my map, whatever my hash map, hash table, whatever you want to call it, right? And now you've got access to the keys, which are strings, and the values, which are whatever the type is that you defined. Actually, I think you can define keys as different types even. You can actually use not just strings, but any type of data. But I'm going to just use strings. So that means we need to store both the key and the value. And if we're storing strings, we can't just store the hash of the string and then reverse the hash. Well, maybe we could do that, but I don't know how to do that. Pretty sure you would need, anyway, I'm not going to even think about that right now. So I'm just going to say our implementation needs to have some way to set the maximum length of a key, because we're just going to do a string to some type. So I don't really care what the value type is. The input type is always going to be a string. And then maybe in another stream we can change it so that you can have arbitrary types as the keys. So yeah, let's see. So I know for sure that we want to have something like map insert, and then you pass in a pointer to the map and a key and a value, and the key and the value need to be stored somewhere. So they're copied, they're actually copied. So we're not just using pointers. Although I think using pointers would be much easier. But anyway, we couldn't guarantee any kind of performance if we use pointers, which might be fine. But let's just say we're gonna copy them. And then map get, same thing, except without the value, and that returns a value. And we want map delete, I guess. I don't actually think we need this. Let's just focus on insert and get for now, and then we'll think about the other ones. All right, so I hope that explanation was sufficient. I didn't actually tell you why. So why would you want to use a data structure like this? Well, sometimes it's really nice to be able to just look things up by a name. Hash and int, the real one, you hash int. Sorry, I just got a comment. Piotr says, usually you have two keys, hash int and the real one that. You use hash int for fast comparison, and then if matched to compare the T key type, which can be string. Oh, I think I understand what you're saying. So, so you're saying we could have something like, don't worry about how this looks, just think about the concept. Something like this. Well, we've got in our data, we've got a hashed key and a key and a value, and then we could compare these ones quickly. Is that what you're saying? Or are you saying that we would compare the, yeah, we couldn't compare the index because we can't guarantee the index. No, that's okay. No, your spelling is fine. All right, so Piotr is saying we should store the hash key and the key. I actually like that. So we'll do that. We'll store the hash key and the key and the value. And I'm going to do a really stupid thing. Well, maybe it's not stupid, but I'm going to make as part of our API that we have a, in our map type, we also have a max key length, which we can then use to allocate the right amount of bytes to store our strings. So that way we don't have dynamic allocations randomly in an arena or somewhere else on the heap. Cool. So apparently, yes, we store this and then we compare string to make sure we have not duplicated the hash. Oh yeah, I see. Right. Oh, I see. So when we're storing it, we still have to compare to this, but when we're getting it, well, what happens if we have a duplication? Okay. Piotr says, or you can just enforce something reasonable small, like 16 byte string. Yeah, that's possible. All right. I'm going to start out with the simple version first, and then we'll think about this. I'm sure it will become more clear as we get into it. But that's the explanation. Oh, I didn't finish my why. Why might we use this? Because, okay, let's say we've got a bunch of textures in our game, right? So we're making a video game. We store a bunch of images as textures, and they all have some data like ID, which would be, depending on your graphics API, the texture ID. So it would have like an ID, a width, a height, maybe the type of pixels that it has. So it could be RGBA8, or it could be BGRA8, or it could just be RGB. Anyway, a bunch of the different things that you might want to look up at some point when you're drawing with the texture. But you don't want to just store them by ID. So you want to maybe store them by name. So you might have like a texture map, which is not the same as a texture atlas. I'm just talking about this kind of hash table. So let's say texture table, and then in there you might have like player with a player string, and then that points to this, and enemy one, whatever, right? And then when you want to use these in your code somewhere, you look up like, oh, I need my texture table, I need my enemy one texture for this, blah, 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 right? That's just one example of why you might want to use a hash table. So let's get into the code. All right, so last time we implemented a queue, and that was working pretty well. I think we'll just add another thing down here. So we're going to write the API first. I'm going to call it a map. Map equals map create, and I'm going to say we can create a map with a particular size. So that'll be the size. We'll just make 10 values. A particular type of thing we're going to put in there. So let's say we're just going to store signed 64-bit integers for now. So just size of signed 64, and a maximum key length 32, an allocator. So we're going to pass in our permanent allocator. And what else do we need? Is that enough? I think that will do, but let's see. Okay, now we're going to make a new file. We're going to say, if we haven't defined map included, then define map included and if. Should make a macro for that. Piotr says, hash code is a first step for fast search. Then if you match the hash, you need to make sure the hash is not duplicated, so you compare it against the string afterwards. Right, yeah. Okay. I understand. Cool, so we're going to return a map. We haven't made one yet, but let's see, what would that be? So we need somewhere to put the data. So we'll call this data. We need somewhere to store the keys. I guess we could store the keys in the same place, or should we store them separately? These would be U8s. Okay, we need a element size, which is this parameter. We need a length, No, do we need a length? We need a capacity. I don't know if we need a length. I guess we should keep a length because then we can tell if it's full without searching the whole thing. Maybe length is the wrong word. Maybe used. Yeah, that's fine, I guess. 32 is referring to the key length allocator. And what is this? What's the problem? Oh yeah, this is right. So this is going to be the capacity. And this will be the element size. And, oh yeah, the maximum key length. Okay, and the allocator. We need to import memory.c, there we go. Okay, let's see. So we're just going to set up this map with our values that we passed in. Pretty straightforward stuff. Result.capacity equals capacity. And max key length, max key length. Now we need to allocate the memory. So data is going to be element size times capacity. That's only going to store the values. So maybe I should call this values. What's the problem here? Oh, yeah. I need to actually make it. So we're going to make a buffer of bytes, which is U8 in my estimation. There we go. And we're going to set the keys. So we've got a max key length, which means we can make strings. There's a bit of a problem here. Okay, I'm going to make a note. So the problem is, in C, strings are null terminated, which means they have an extra 0 at the end. So if we only allocate exactly the amount exactly the right amount of bytes, then they won't be null terminated unless we add a byte in between. Or I suppose we could do that. So we could say keys equal max key length plus 1 times capacity. Right, so now I'll just make a little diagram here. So let's say our keys were 3 long, like they were in this little example. You could imagine our memory is like this. And then we've got our first key, ABC, and then we're going to have to skip this byte, and it will be 0 by default, because our memory allocators always give us 0 memory. And then D, E, F, 0, and then whatever, QOP. So we've actually allocated an extra, I don't know why I drew a Q there, probably because anyway, we've actually allocated an extra byte for each key so that we can make sure that there's a 0 at the end. Yeah, I think that's fine. I'll just say, I don't need a note in that case, I guess. Alright, I think that's okay. We'll go with that. So, the annoying thing is now we can't just advance by max key length. We have to advance by max key length plus 1, but I guess that's not really a big deal. But now they're not going to be aligned. Whatever, doesn't matter. Strings aligned to 1 byte is fine. Okay. I think. I'm not going to think about it right now. Let's just get the functionality working first. All right, so we know we want this API, map insert and map get. Okay, so we're going to insert into our map. And we're going to insert a key, which I'm going to use our string. We've got a string type. It's called str8 because it's Piotr says hash tables are hard to make right. So many decisions, open or close, addressing, collision resolution, balancing threshold. And in the end, you'll say, I'm going to use an array. And that's probably true. I'm probably not going to use a map very often. But I just thought it'd be a fun exercise anyway for a stream. Even if it's not, I mean, obviously it's not going to be optimal for anything. It's just for learning. We want some data, so that'll be our value, map key value, that's correct. And we're going to return a pointer to the value, I think. Yeah. And we'll have a map get, which will be something like this. We'll return a pointer to the value. Okay. All right. So let's try to insert something. So first, we're going to need to hash it. We'll hash the key. Okay, so we're going to hash the key, which means we need a hash function. So I'll just call it map hash, I guess. This will return not an int, it will return a usize. And it will take in, we'll just make it take in a string. And we're going to do something really silly, doesn't really matter for our purposes. I'm going to keep saying that in case you think I'm saying it doesn't matter. It doesn't matter for our purposes right now. We just want to get something working. So why am I using a loop? Oh yeah, I is less than k dot length. I plus equals 1. I do have a migraine right now. Luckily, it's not too painful. Yeah, fnv hash function is good enough, says Piotr. I don't know what that means. I'm just going to use some prime numbers and then multiply the string values and then see how that works. So I want to say result equals 0. K dot data I, so this is what we're up to, result plus equals times, what are some prime numbers? 51 times 31, 31's prime number, right? Yeah, I think so. 17, that'll do. And then I'm just going to leave it like that, and then I will, yeah. Wait, is that right? Yes, yes, yes. So basically we iterate through our key, and on each letter, I should probably change this actually. So this needs to be cast. I'll use the cast. I'm going to cast this U8 into a U size so we have enough space. I think Piotr's going to write a hash function in the comments in the chat, so maybe we'll use that instead. But Yeah, so basically what we're doing here is we're iterating through the string, getting each character, casting it to a U size so that it's larger than 8 bits, so that we can multiply it by these large numbers, and then adding that together until we get some kind of result. And the reason we use prime numbers is, I believe, they're just, what's the word? More random is not the right way to say it. I don't know, I'm not a mathematician. Or, you know, I didn't really get past high school mathematics yet. I'm working on it, but not yet. I'm sure there's a reason, but I think they give less deterministic results, if that makes sense. So we're going to say our hashed key, or just hash, I guess, is map hash, and we're going to pass in the key. Fantastic. And, oh yes, this is very important. We're going to have to use the modulo to basically wrap it around, if that makes sense. So we're going to wrap it back around to the capacity of our map. Piotr, did you post something? I don't see anything in the chat. I just see that you said you can yoink this and then good hash redistribution in table. Or are you answering what I was talking about with the prime numbers? So what this does, the mod and capacity, is make sure that we stay within the range that we've set here. So, you know, if we had like a 5 and we modded, if we got a hash back and it was a 5, and we mod it by this value, it would be wrapped around to 0, I believe. Okay. I'm gonna make the text a little bit larger, just why not? So we've got our hash. It's not a very good hash, but that's beside the point. And now we want to use that to index into the table, which is an array. So we'd say something like map values, and this is a pointer. So we're gonna have to convert it into a byte pointer so we can do some arithmetic on it, plus element size times hash. So maybe this should be called index. So this is an index. We're just going to get a really simple version working that has no collision protection yet. And we're going to say this is our pointer. I'll just use U8 again. Pointer equals this. It actually could be anything, right? Yeah. And then we want to put our data in here. So actually I will make this void pointer. Memcopy. Luckily we have that function. Oh, by the way, I was looking at the Win32 intrinsics for anyone who was here last time. Some functions seem to work and some don't. Like memcopy works. What was the one I was looking at? I can't remember. I think it was memcompare, MEMCMP. Apparently, even though it's an intrinsic, I can't get it to work. It's a bit unfortunate, but oh well. Okay, so we got memcopy, and we're going to copy into our pointer, which I'm going to call destination actually, or dest. And we're copying from our value, and we're going to copy an element size element. So that's going to copy our data in. That's great. Aryan says, hey, hello, hello, hello. How are you doing? So this should copy our data. Great. So we've got this part hopefully sorted. We haven't copied our key anywhere. But let's just test this. So we don't want to program too much without testing anything. Let's see if this works. So we need to import our map. Compile's good. Today we're going to be using remedy BG instead of the rad debugger because there's still a little bit of a bug with virtual allocated memory. So that's unfortunate. I do like the rad debugger, but I also like remedy, so that's fine. Okay. All right. Oh yeah, I didn't actually put a break after this, so just gonna exit the scope. Oh, we've got our data here. That's good. Let's have a look. That's the stack memory. That's fine. We want, where is it? Values. Yeah. What? Go to memory window. There we go. Well, there's nothing in there yet, so that makes sense. Let's try map insert. M. No, it's called map. Map. Key is going to be key, very descriptive, and we're going to insert a signed 64. I haven't looked up why this works yet. It's a bit weird, actually. We'll just insert the value 54, I guess. Actually, I'll use hex. So 0x54. That way, when we look it up in the memory window, it'll be this. Don't have to do any conversions. This is weird. I haven't looked up why this works, but you can kind of cast, I guess this would be an anonymous struct or something, into an S64 and then get the address, like all in one spot. Don't know why that works, but it does. I'll have to look it up. All right, let's have a look. Okay, we'll go in here. I didn't actually, let's have a look what we got. We got index 3, great. Let's see if we can get the destination. All right, we got something. We're copying some data into it, and there it is. 54, the capital letter T. Well, that's good. So, we seem to be inserting things, inserting data into our hash map. Let's see. We have no protection if I put in something that is really long here. Lol, ha ha ha. That's probably longer than 32 characters, right? Yeah, I think so. So that's just going to put, okay, that got number 4, I guess, index 4. But that, you know, that should not be allowed. So we're going to say an insert. Do we disallow it or do we truncate it? There's no, I mean, if we're just going to return a void pointer, there's no information if we just return nil. Like it doesn't say, is the thing full or you know, was the key invalid, or is there a problem with the value? Is the value the wrong size? Well, we don't know what the size of the value is, but yeah. Maybe we should make a result type. I don't know. Something like this. Assert during debug and truncation in release mode, says Piotr. Piotr? Am I saying that correctly? Yeah, I do not mind having asserts. So we could say, I think we already have an assert actually. Assert k.len less than or equal to max key length. Almost, but Peter is fine. I mean, I would rather pronounce it correctly, but sure. Okay. So now we should get an assert error. And let's have a look. Do we? Yes. So we've got an error here. I wonder if this is going to work. Can I say and I mean, this is very clear. I don't think I need to add a comment here. The length is less than or equal to the max key length. Very obvious. Don't need to add any comment. That's fine. Okay. So that's that thing done. Now we need to store the key somewhere. So the key would be, I suppose, keys plus yeah, okay, fair enough. Piotr, I'm gonna just keep pronouncing it like that, I'm sorry. That's how I can read it. Imagine me trying to explain to you how to pronounce my name on the stream chat. Yeah, that's fair. What was I doing? All right, so we've got our values copied in here. Now we need to get the position of the key. So it's going to be basically the same, but it's going to be the max key length plus 1 times index. Memcopy, and we'll put, I'll make this key destination just to make it very clear. I'm going to copy in the key.data and key.length. So actually storing a C string rather than our own normal string type, because we already know what the max key length should be. So I think that's fine. We don't need to store it as a string. It would be like a string in place anyway, because anyway, it doesn't matter. I was going off on a tangent. So basically we've got data being inserted. Let's check if the key gets inserted, and then we can move on to dealing with collisions. All right. Right. So of course that's not going to work because this is too long. Okay, that looks like the keys here. Is that correct? Yeah. So there's one down here, and there's one up here. Yeah, see, they're totally not aligned, but whatever. I wonder if that's a big problem. That's interesting. I would have thought that, oh, these are actually getting, oh, it's a different, never mind. It's a different key, so we got a different hash, which means we got a different index. So that's index 3 here, and then 4, 5, 6, 7, that's index 8. So I've got 3 and 8. I kind of don't like that they're not aligned. What if we did it like this instead? If we got the max key length, and then when we allocate the space, we allocate enough space for to make it aligned on an 8-byte boundary. Would that make sense? 8 bytes? Okay. No, I'm getting hung up with the details right now. Let's just get it kind of working first. All right. So our keys are in there, our values are in there. That's great. Now, how do we get them? How do we get them out? How do we search for them? Well, we basically just use this hash function again, and then we just look them up. So same as this. So this would be result equals blah. And this should just work, but of course it's not going to be bulletproof, because why did I type result? Because it's not going to handle collisions. So we're going to have to do that as well. So we just pass in key, and I will call this S64 key value. And what's this? Well, I'm just going to actually name these V1 and V2 to make it a little bit easier on myself. I don't like naming things. Here, lol, haha. Excellent. No, ha ha ha. Alright. Now, if we run this, we should have inside here the value, what, 84? Ah, 0x54. Is that 84? Oh, I thought hex was a thing. Is it X? Yeah, there we go. V2 X, there we go. 0x54. Why did I give them both the same value? I shouldn't have done that. Let's make this one 24. Alright, there we go. Cool. So we are getting the values back out, which is perfect. That's what we wanted. But, of course, as I alluded to, there is going to be a big issue. So if we go down here, put another debug break, and then we insert a bunch of stuff. We're not going to use the same key. And we'll just increase the values perhaps. So I'm going to make this 14, 24, 34, 44, etc. 54, 64. Okay, and now we've got to change the keys as well. I'll just type in random characters. And that's probably going to come up more than once. Okay. Now, let's have a look. So we've got our results as they were. Let's have a look at the memory here. So as we step through these, we should see some of these values being overwritten. Let's have a look. Okay. Alright, that one was okay. That one was okay. That one was overwritten, I think. That one's okay, that one's okay. That one was overwritten just then. So obviously we don't want that, right? That is not ideal. You don't want your data to just be overwritten. So now comes the hard part. Collisions. Let's see. So as I said before, I just clicked the wrong button. We're going to go with this version, which I think is open addressing. I'm not 100% sure. where basically if we have a collision on collision 3, on key index 3, then we're going to go to the next one, and if it's empty, we'll put it in there. And that means when we hash something else and it comes up with index 4, we're going to try to put it in here, and something's going to be in here, and then that's going to be actually put up here if this is available, right? And etc., etc. So we might end up with a linear search in the worst case, which is kind of funny, because then why didn't we just use an array, I guess, or a pair of arrays? Linear probing. Is it called linear probing? Okay. Maybe I'm getting my terms wrong. I apologize if anyone is getting triggered. So, yeah, I mean, the funny thing is we probably could have just allocated one table with keys and then one table with values next to each other in memory. So we allocate them right next to each other. So they would still be relatively close. And then you just linear search the keys. Or maybe, yeah, linear search the keys. Actually, sorry, maybe hash the keys and store a hashed version and then the key, and then just linear search them until they match, and then when they match, compare the key, and then just index into the other array. I think that would actually be totally fine. Piotr says linear probing is fast because of the cache, but then there is a risk of clumping values if the hash function is bad. Yeah, that makes sense. I actually like this design now that I just said it. It's so much simpler. Maybe we should have gone with this. Well, we can always build another one, right? Cool. So what we're going to do now is oh, I didn't actually clarify. So in this design, the hash wouldn't be the index. You would just basically insert in order. So you do in order insert, you'd insert the hash in the key, and then that would just be mapped to the data. Or you could just insert the hash, the key, and the value like this. Hash, key, value, or hash, key, value, and then these would be separate arrays. So if you wanted to iterate over the array of the values, they'd all be all next to each other in memory. And if you want to iterate over the keys, they'd be all next to each other in memory as well. And then you could still have your lookup by name or whatever, and it would be reasonably fast, I think, depending on how large your data is and all that kind of stuff. Piotr says hash table with one indirection to a fixed array of values could be a good strategy. If the hash subarray is full, then you need to resize and rebalance the hash table. Right, yeah. In general, in this code base, we're not doing resizing at all. So if we look at the allocators, they have no resize functionality at all. So we just allocate stuff, and then so we're going to make liberal use of pools. So pools don't need to be reallocated to a bigger size, because you just allocate as many as you think you need, and then you can just recycle the elements. Arenas, you'd usually just reset the position to 0 when you're done with all the memory that's in there, so you can make arenas for different code paths and stuff. Yeah, I'm trying to get out of the habit of using resizable stuff all the time, just for fun. And let's see what happens. So we're going to go with the original idea, which is sorry, I'm losing my train of thought here. Piotr says no to allocate new bigger memory, and then you go through each item and add it to a new hash table. Oh, I see. So every now and then you might need to copy the data. Obviously you'd want to make your hash table big enough at the beginning so that you wouldn't need to do that very often, as few times as possible, while keeping memory as close to each other as possible for the performance gains. That makes sense. All right, so we need to check if the thing at the index already has a value in there. So we can do that by basically checking this, I guess, the key, or would we check the value? I think we'll check the key. We'll just leave the values in there, and we'll just remove the, we'll zero out the keys when we delete something. So if we say this is actually a string, right? Then what do we check for? We can check if this is 0, then there's nothing in there, right? Piotr says that's why linear search in array is still faster, even up to 10,000 entries. Also, C++ gurus have been telling. Yeah, that's a very arbitrary number. I agree that linear search is fast and fast enough for a lot of cases. But let's say, for example, you need to search, and your search is matching data that's like, what's 10,000 times 1,000 times? You know, if it's more than like a couple of hundred bytes that you're matching, then you're going to run out of your cache pretty quickly. So the 10,000 number doesn't really make sense. Maybe it's an okay rule of thumb, but really they should be saying if the size of your data is smaller than your cache, then it's going to be fast, right? Anyway, so if we dereference this, can it ever be, it can't ever be null, right? Because the index is wrapped around. Okay. So that's how we know if it's empty, right? So if this is empty, then we do this. Okay, let's just try this first. And we'll run through our step by step, do our little experiment, and we'll just see if anything gets overwritten. Okay, so we'll keep an eye on the right side of the window here. I find it easier to look at this because it's in English, I guess. And we'll just have a look. Nothing got overwritten. See, so that didn't even get inserted because it would have overwritten, I think, WFP, right? So in that case, I mean, we don't have collisions now, which is great, but we're also not able to insert something with a particular key if we've inserted something else with a particular key, and that's not great. So in this case, we're inserting, but you know, we could say, maybe for a while key dest is not equal to 0, key dest equals I'll explain this in a second. That might be a problem actually. This should be a for loop. Alright, so basically what we're going to do is yeah, I guess that's fine. Not too happy with the structure, but that's kind of beside the point right now. So basically what we're doing is we're going to iterate through the entire array of our hash table. And we're going to search, this should be at the bottom, we're going to search for an empty spot, and if we find one, then we're going to do our thing, we're going to break out of this loop, and that's all great. We didn't set result anywhere though, so we should do that. This should actually be result. There we go. That way we don't return nil all the time, so the person can check the value when they get it back. Right. The person, which is going to be me, I guess. So what are we doing? So we're basically checking if the spot is empty because the first byte is 0, then we're going to do our thing and we're going to break. If it's not empty, then it will run this code here and it will increase the index by 1. And then it will set a new key destination, which we're going to check on the next loop. And then we'll keep going, going, going. And then if we get through the whole capacity, this is wrong. This needs to be index equals index plus 1 mod m capacity. Otherwise, we'll run off the end of the array and we'll be checking random data. We don't want that. So this is going to wrap around. And then we're all good there. Yes. Cool. I think that's fine. So let's have a look and see what happens. Did I compile it? Did now. All right. So let's have a look. Going through. Okay, so this next one, key YRUJ, that one was a collision last time. Let's see what happens this time. There we go, it got added here. That's great. That's what we wanted. And then ABCDE gets added, and then what happens with this one? Nothing and nothing, because it's full. So that's fine. Do we want to assert when a map is full? Maybe we do. M m used is equal to m capacity. Now, of course, we haven't actually updated m used, so we should do that here. By the way, I have a rule. You probably noticed me writing this like plus equals 1 all the time instead of plus plus. I increment numbers like this, and I increment pointers with this operator here. Just makes it easier for me to quickly tell what I'm looking at. Okay, so that's all good. And if it's full, it's going to assert. Let's just check that that works. That did not work. Why is that? What's the capacity? Used is 0 and capacity is 0. Did I not compile? Probably didn't compile. There we go. Great. Piotr says, there's nothing stopping you from having an additional array of keys and search into that first. And also, he thinks the most underestimated data structure is sparse set, which can be used with ECS or in ECS with good results, and it's way less complicated. I'll have to look up what a sparse set is, although I think I have an idea in my mind. Yeah, but I have to look that up to be sure. All right, so we don't have collisions. We have an assert when we're full, and we try and add something, which I don't know if that's great, but we're going to leave that for now. Now, the next thing we need to do is make sure that our lookup function, our get, can actually handle these collisions, because if we go to our code here and where's the code, and we do something like S64 v3 equals map get, and we copy this one. I forgot quotes, there we go. So this, what is this going to give us? It's going to give us the wrong thing, I'm pretty sure. Let's have a look. I'm going to just disable this assert for a second. And we'll start again. There we go. So we got back v3, and I'll put it in hex, and we got 0x64. What is 0x64? That is this one, ha 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 ha, WFP. That's totally wrong, right? Because when we inserted this and it collided with where this was inserted, and then when we used the get, we didn't do the search. So we need to go, and unfortunately we need to search through somehow. So let's think about this. So we've got our data. Where is it? Here. And we had our collision. And there's something in there. So we've got to check. Okay, so we actually haven't stored the hashes anywhere. So maybe we should do that. But for now, we'll just look at the keys, okay? So we're just going to check the keys themselves, which is going to be slow. So what we need to say is I is less than capacity, I think. So we're going to loop through all of the elements, starting at index. And we're going to say result is not equal to this. This is just value. We don't even need to do this right now. We need to look at the keys. So key equals keys plus max. Yeah, max key length plus 1 times index. And it's basically the same as this. Alright, so we'll just grab that. I'm going to actually put this up here, and it's not going to be key destination this time. Actually, no, we don't need to put that up there. That's fine. So this is our key. Now we need to match it to the key that we passed in. And because I don't have access to the standard library, I think there's something in Win32 for this, but for now I'm going to do something a bit silly, which is just do a loop, I guess. Let me see. I'm going to have a look at Win32 intrinsics, and I'll bring it onto the other screen in a second. When I can find it, x64 intrinsics list, is this what we want? Intrinsics available on all architectures. Here we go. So, you can see that a bunch of functions are supposed to be included, like memcopy, which we are using. So if we look at memcopy, I've actually just defined it in here in types.h, and it works. I know this build command is a bit crazy, but you can see no default lib, right? So that means no C standard library, but memcopy still works because it's included as a compiler intrinsic. But I'm pretty sure if I use memcompare here, it's not going to work. So it's an int, and it takes 2 constant void buffers and returns account. Okay. So returns int, and an int is s32, I guess. Memcompare. Actually, I use the original type. Memcompare, not pointer. And what was the other thing? Was it a long? I think unsigned long. Okay. I'm pretty sure this is not going to work, but let's see. And where were we? Map. So memcompare, we're going to compare the key and the key that we pass in, and it's going to be this length, and we're just going to say difference equals this, and wait, what was that? Yeah, unresolved external symbol memcompare reference in yada yada yada. So maybe it's in a different library or something. Or maybe we just can't use it. But it's supposed to be an intrinsic, that's why I'm confused. Isn't the whole point of an intrinsic that UCRT intrinsic? They have intrinsic forms on all architectures, right? So we can use memcopy, we can't use memcompare. Why? They're in the same header. I don't know. And I'm not going to figure it out right now. So what we're going to do instead is something stupid. Well, something straightforward, let's say. And we can say, I'm not going to be too clever about it. I'm just going to write a for loop. J equals 0, j is less than k.length, j plus equals 1. If key j is not equal to k.data j, then break. Yeah, I think that's right. And I'll just set a boolean to false or true, I guess. Matches equals false. Alright. Brain dead. Simple. Shouldn't have an error, but also very slow. That's fine. We're not doing this for performance right now. We're doing it for learning. So we're going to iterate through each key, match each character, and if the character is different, then we're going to say that they don't match, and we're going to break. That's it. And then down here we can say if matches. So this is our next, I guess, block of code that we need to do. So if we've got a matching key, then what? We return it, right? Result equals m, what do we call it? Values. Values plus m element size. Oh, it's right here actually. Excellent. And I guess we'll break here as well. I think that will work. I'm probably forgetting something, but let's have a look. Step through the code, do the compile, yes. Okay. So if we get up to this line here, oh no, we need to get up to the end. So here we are. All of our data is in there. Nice and unaligned. It's very annoying. And if we get this, what do we get back? We get 0x94. That's correct. All right, so that worked. That's great. That's what we wanted. Now I'm going to fix this data alignment because it's really bugging me. So anywhere we do max key length plus 1. Yeah, I don't like it. I don't like it. And I'm going to put a note saying max key length is 1 byte less, space for null terminator. Oh God, I hate that. I've got this annoying bug with Helix where the line after a comment is always, the first character is uncommented for some reason in my highlighting. It's really annoying. It's only in C with the ClangD LSP, I guess. Anyway, probably don't need to put note again. Space for null terminator. Example, key length of 32 is actually 31 characters max. That will do. We need to change this. Okay, I think that will work. Let's see. There we go. Isn't that much nicer? It's all aligned properly, you know? Of course, whoever makes the map could just put in a weird number, like, I don't know, 19. And then what's going to happen? It's horrible. Oh, it's horrible. But who would do that? No sane person would do that, right? Everyone would put in like 32, 128, 256, or something like that. I think. Doesn't matter. Point is, we have a working hash table. Kind of. I mean, well, it is working, isn't it? Do we miss something? Oh, we can't delete things. All right, let's see if we can delete stuff. All right. Map, delete, pass it a map, and we need a key that we're going to delete. Whoops. And we won't return any value, I guess. Or I guess we could return a boolean if it worked or if it didn't work. So basically we need to use map get. And we'll say our value is here. Okay, pass in our map, pass in our key. Very nice. And if v is not equal to null, then we got something out. Then what can we say? I guess we'd say the key is going to be... Oh, hang on a second. That's not what we want. We don't want to use map get. We just want to use the hash function, like this. Or do we? No, this is annoying because it might not be at the same position, and there's no way for the value to tell where the key is. I think. Is that right? Let's have a look at the data. So this one is annoying. 1 second. Still need to do a manual search, says Piotr. Yeah, I think so. Just gonna get it straight in my head first. This migraine is starting to get bad now. Okay, let's see. So these are our values. These are our keys. Our keys, like what? Let's see. 4 is this one. C4. Where is C4? I don't even see C4. Oh, this one didn't get added because it was full. Okay, 5 4 1 4 2 4. 1 4 is here, but it's actually... Oh, it's not expanded enough. Piotr says, since we are searching, we might as well pass a pointer, just in case anyone would like to have a result and remove it at the same time. Are you saying a pointer back to the value so that they can zero that memory if they want to? And rename it to try remove. Yeah, I suppose. That is more accurate because it doesn't actually delete anything, and it also might fail. So yeah. Let's see, 17. What are these values? I think this is from our queue. So a map starts here, 34, 54, 74, 14. Piotr says no, user passes their own pointer and we copy the data before deletion. Okay, why would we do that? I'm not really sure why you'd want to do that. Wouldn't you just instead use get and then copy the data and then use delete? Maybe it would be handy. I don't know. I'll have to think about it. Alright, so we still have to search for our delete, which basically means this thing again, right? What was that? It sounded like something just hit my window. Piotr says if you do a get and a delete, then you have to search twice. That's true. In that case, I would rather make another function called like delete and copy or something like that, because you wouldn't just expect your delete to copy data. I think that's a bit strange. But yeah, I think what I'm going to do is actually cut this out of here. And can I make this into a function that they can both use? Let's see, key. So we want to match the key. Yeah. I guess we could say map get index and pass in the key, and we would get the index back. So that would be basically this. If the pointer is null, you just ignore the copy. Okay. I'm still not convinced about that one. So in this case, index should be Piotr says if I want some inspiration, he highly recommends looking up C# dictionary interface and what methods are available. Okay, I might do that. We're going to return the index here. I'm not trying to be difficult, by the way. The whole point of this stream is that we... that doesn't make sense. The whole point of the stream is that we are trying to do stuff from scratch without looking things up. I know that seems kind of weird, but yeah. Try remove with copy is really important if you have a concurrent version of a hash table. Oh yeah. I see. Yeah, we're going to touch concurrency a little bit later. I don't know if I'm going to use a hash table, concurrent hash table. I haven't thought about it. Definitely queues though. Queues are very good. That doesn't make sense either. I don't want to return a signed 64 and return -1. I don't like this because, well, I just don't like it. I don't like the idea of indexes being negative. It doesn't make sense, but at the same time, I mean, what would the value be? I mean, in another language, you would return like an index and a boolean saying whether it was okay, you know, or like this or something. In Go or Odin, you would do that. In Rust or Zig, you'd probably return a result type. I think a lot of people in C would probably do something like this. Bool, okay, and then you could say okay equals false. I don't really like that either, but Piotr says you could even pass RW lock on initialization or null if it's a normal hash table. Just giving some ideas which I use in my collections. Yeah, I appreciate that. Alright, I feel like I'm overcomplicating this right now, and my brain is starting to not work from the migraine. So I'm just going to copy this. So we can get this going. Alright, we're going to do our search. If the value is not equal to null. Why are we doing this? We need to find the key. Okay, so we actually don't need that part. We need all of this. Yes. I'm going to, okay, if we match here, then we don't set the result. We actually set result equals true, and we want to remove this key, zero out the key. So memset key, and then max key length. Oh, right, so 0 max key length, basically. I think that should work. Did I actually write a function? No, didn't call it. So let's try to delete, well, this one, I guess. Map, and we'll just copy that again. Okay. Okay, here we are. We've got our value. Let's go to the memory. Oh, that's not the right place. Can I have a look here? All right, so we're gonna apparently delete this key here. Piotr says if you want to deduplicate search function, you can have a function that does map find key index and returns index or -1 for non-existing key. I did actually just write that whole function and then deleted it because I didn't want to do that. There we go. That works. Fantastic. Maybe I should just get over that and just use signed 64-bit integers for indexes. Because no one is ever actually going to use, probably. I don't even know what the upper limit of a positive signed 64 is. I think it's a very large number. I believe this website has searches, not searches, limits, right? Oh, that's not. Yeah, integer limits. Here we go. So, I mean, we're not going to have a hash table that's that big. So maybe it's fine, and I should just start using them. All right. Anyway. I think we're in a pretty good position now. We've got a rudimentary hash table. It adds stuff. You can add your data in there and do things. That's great. Let's have a look at... hang on a second. This is not the right thing. Here we go. I don't want to leak random stuff. I got personal things in here. This is what we've been following so far. So I would say for hash table, I'm going to mark this as green, as in it's functioning. That's the wrong one. It's this one, isn't it? There we go. We haven't made an array yet. So in C, I mean, we've already got arrays, but we want to make an array where we can append things, and not a growable array, so it's not dynamic in size, but it's like a fixed size array that you can append values to, and you can remove them from and sort it and reorder it and stuff like that. So we'll probably do that at some point, maybe next. Our pool we need to fix still, so we'll probably do that. And then I want to move on to, I think software rendering would be one of the next things. So if that sounds good, then please make sure to subscribe so you get updated to whenever I go live, which should be around 7 to 8 a.m. my time every Saturday, Tuesday, and Thursday. And now I'm going to go work on my course. So I've got a lesson that I want to put out today. And if you don't know about my course, I actually teach, so let me just start that again. In this stream, we're doing like all this stuff that we expect the language to already have, building arenas and string builder. The string builder is pretty fun. Queue, hash table, writing to files, reading to files, all the stuff that modern languages just do for you. That's kind of the point. Just taking a look under the hood, trying to implement things, having some fun. But I actually teach a course on how to use Odin and Raylib and building games from scratch. Well, it's not from scratch because we're using Odin and Raylib. It's not as from scratch as this, but so far we've got about 30 lessons in the Metroidvania section done, and then we're going to move on to an RPG. We're just about to start building a custom level editor, which is going to be pretty fun because we're going to get to design a binary file format and have like a bunch of integration with the game, so you can press F5 and start editing while you're playing the game and things like that. So that'll be pretty cool. That's what I'm going to be working on today. So if that sounds interesting, then check it out. If not, then I will see you next time, hopefully, and I hope you have a great day. And thank you, Piotr, for all your suggestions, and I will catch you next time.